the metal that protects all other metals from rust. Picture this: 70% of the world's steel is covered with a thin layer of zinc. Bridges, skyscrapers, cars, ships, everywhere zinc stands guard, taking the hit from corrosion. Every second, the world produces 1.5 tons of zinc, 14 million tons per year. It's the fourth largest metal by production volume on the planet, after iron, aluminum, and copper. But they extract it unusually. Zinc is vaporized at 1,800 degrees Fahrenheit, and the vapor is collected. Yes, the metal turns into gas. How do they turn gray ore, mined a mile underground, into a bluish-silver metal that sacrifices itself for others? You'll learn why the ore burns in furnaces, how they collect metallic vapor, and why without zinc, the entire infrastructure of the planet would collapse. Watch to the end. The finale will show what's behind every galvanized beam. This is the story of the bodyguard metal that took on the corrosion of the entire world.
A mile underground, darkness, explosion, tons of rock crash down. This is a zinc mine, one of hundreds around the world where ore for the guardian metal is extracted every day. Underground dump trucks with 50-ton capacity haul ore to the mine shaft. An elevator the size of a house lifts the rock to the surface. The ore is dark, almost black. This is sphalerite, zinc sulfide. Crystals with diamond-like brilliance, but the metal content is only 10 to 15%. The rest is waste rock. Trucks carry the ore to the processing plant. The transformation from stone to metal begins. Massive cone crushers as tall as a 3-story building grind ore chunks the size of cars. The noise is deafening. The rock is crushed into gravel the size of fists. Then the gravel goes into ball mills, rotating steel drums 16 feet in diameter, filled with steel balls the size of watermelons. The drum rotates, balls fall, grinding the ore into fine powder. After 8 hours of grinding, you get gray dust, particles the size of sand grains. The ore powder is mixed with water, creating gray liquid slurry called pulp. It's pumped into huge flotation machines, tanks with volumes of 3,500 cubic feet. Chemical reagents are added, foaming agents and collectors. Mixers are turned on and air is fed from below. The magic of flotation begins. Millions of air bubbles rise through the pulp. Particles of sphalerite, zinc ore, stick to the bubbles and float up. A gray foam forms on the surface, 20 inches thick. This foam contains zinc. Waste rock settles to the bottom and is drained off. The foam is collected, filtered, dried. The result is concentrate, powder containing 50 to 60% zinc. From 100 tons of ore, you get 10 to 15 tons of concentrate. This concentrate is loaded into rail cars and shipped to the smelting plant. There begins the real alchemy, turning powder into molten metal. And this is a process where metal turns into vapor. At the plant, concentrate is loaded into fluid bed roasters, massive steel cylinders 66 feet tall. Hot air under pressure is blown in from below. The concentrate powder lifts up, floating in the air like dust. Gas burners are ignited. Temperature rises to 1,650 degrees Fahrenheit. The zinc sulfide ignites. Yes, the ore burns. Sulfur oxidizes, releasing enormous amounts of heat. Sulfur gas flies up the stacks. It will be captured and turned into sulfuric acid. And zinc sulfide transforms into zinc oxide, a gray-white powder. The temperature in the furnace is so high that the walls glow red. The roasted concentrate, zinc oxide, is cooled and mixed with coke, crushed coal. The proportion, 3 parts oxide to 1 part coke. This mixture is loaded into vertical retort furnaces, steel towers 50 feet tall, lined inside with refractory silicon carbide. Heating begins. Temperature starts climbing. 1,800 degrees, 2,000 degrees, 2,200 degrees. At 2,200 degrees Fahrenheit,
Carbon begins taking oxygen away from zinc oxide. A reduction reaction occurs. But something amazing happens. Zinc doesn't melt. Its boiling point is only 1,665 degrees, but the furnace is at 2,200. So zinc immediately turns into vapor, metallic vapor. Inside the furnace, atoms of gaseous zinc are flying around. The vapors rise up and exit the furnace through piping. They enter a condenser, a special cooled chamber. Temperature in the condenser is around 840 degrees, below boiling point but above melting point of zinc. The vapors condense. Drops of molten zinc settle on the condenser walls, glowing orange. Liquid metal flows down the walls and collects in a receiver. This is crude zinc, contains impurities of lead, cadmium, iron. Purity around 98%. Each furnace produces up to 100 tons of zinc per day. The metal is cast into molds. The result is ingot bars weighing 55 pounds each, silver gray with a bluish tint.
For some applications, pure zinc is needed. Then it's refined, purified by distillation. Crude zinc is heated to boiling in a vacuum furnace. Under reduced pressure, boiling point drops to 1,300 degrees. Zinc vaporizes while impurities remain solid. Zinc vapors are condensed in a cooler. The result is refined zinc with 99.99% purity. This zinc is cast into ingots. On the ingot surfaces, a characteristic pattern forms, crystalline designs resembling frost flowers on glass. This is called zinc flowers. Ingots are stacked. Zinc is ready for use. But its main application awaits in hot-dip galvanizing baths. There, steel products will receive corrosion protection. The process looks impressive, like baptism of metal by fire. A steel beam 40 feet long is immersed in a bath of molten zinc. Temperature 840 degrees. The beam completely disappears in the silvery liquid.
Chemical reaction begins instantly. Zinc reacts with iron on the steel surface, forming a layer of intermetallic compounds, a solid alloy of zinc and iron. This layer bonds permanently to the steel. On top, a layer of pure liquid zinc. The beam is held in the bath for 1 to 2 minutes. Then it's pulled out. Excess molten zinc drains back. In air, the coating quickly solidifies. The surface becomes silvery, matte, with the characteristic pattern of crystals, zinc flowers. Coating thickness from 2 to 8 thousandths of an inch. That's just fractions of an inch, but it's enough. The galvanized beam won't rust for 50 to 70 years. Even scratches aren't scary. Zinc continues protecting. It's about electrochemistry. Zinc is more active than iron. When corrosion begins, zinc oxidizes, not steel. Zinc sacrifices itself, protecting iron. This is called cathodic protection. World production of galvanized steel, 55 million tons annually. This uses 6 million tons of zinc. Without zinc, modern cities would be impossible. 70% of zinc goes to protecting steel. But there are other applications. Brass, an alloy of copper and zinc, has been known for thousands of years. Contains 15 to 45% zinc. Golden, strong, easily worked. Brass is used for plumbing fixtures, musical instruments, cartridge cases, decorative items. Zinc die casting, a method for manufacturing complex parts for automotives and electronics. Molten zinc is injected under pressure into steel molds. The result is complex-shaped parts accurate to tenths of thousandths of an inch. Zinc batteries, still used by the billions. Zinc powder in chemical industry. Zinc oxide in rubber industry, cosmetics, medicine. Zinc ointment heals wounds. World zinc mining, 14 million tons per year. China produces 40%, 5.5 million tons. Peru, Australia, USA, India, other major producers. Zinc price, around $3,000 per ton. The history of zinc as a separate metal began late. Europeans knew brass since ancient Rome, but couldn't obtain pure zinc. The problem: zinc evaporates when heated. Indian and Chinese metallurgists in the 16th century learned to condense zinc vapors in closed retorts. In Europe, pure zinc was obtained by German chemist Andreas Marggraf in 1746, but mass production began in the 19th century. Revolution happened in 1836 when French engineer Stanislas Sorel discovered the hot galvanizing process. He found that immersing steel in molten zinc protects from corrosion. This changed construction forever. Before galvanizing, steel structures rusted within years. With galvanizing, they served for decades. The Eiffel Tower is painted, but many bridges from that era are galvanized and still standing. Today, without galvanized steel, skyscrapers, bridges, power lines, ships are impossible. Zinc, the invisible guardian of infrastructure.
And so, having traveled from explosions a mile deep through giant crushers and flotation tanks, through fluid bed furnaces at 1,650 degrees and retort towers at 2,200, through transformation into metallic vapor and condensation, zinc emerges, the bodyguard metal of modern civilization. The silvery metal that sacrifices itself, protecting steel from rust. The fourth largest metal by production on the planet, without which all infrastructure would collapse. Every time you see a steel bridge beam, a roofing sheet, or a car body, know they're protected by a thin layer of zinc as thick as a human hair. A layer that takes on corrosion, oxidizes instead of steel, slowly destroys itself, saving the structure. This is a story of nobility at the atomic level. How one metal protects another, sacrificing itself. From underground explosions to silvery skyscraper beams, zinc's journey spans several weeks and 2,200 degrees. The metal that vaporizes to protect, that oxidizes so others don't rust. The invisible shield of 14 million tons annually, standing between steel and corrosion. Zinc. This is why bridges don't collapse, roofs don't leak, and cars don't turn to dust in 5 years. The guardian metal, the sacrificial metal, the metal without which the modern world would simply fall apart from rust.
Every year, over 100,000 kilometers of new rails are laid across the planet. And every single one of them goes through hell first. Fire over 1,500 degrees, the crushing force of rollers, and jets of water that cut metal like glass. From scrap heap to gleaming steel, a rail's journey is like an initiation, where every step decides whether it survives or shatters under the first train. But what makes this steel so perfect that it can handle thousands of tons of pressure every day without bending or cracking? Stick around, and you'll see how the arteries that move the entire world are born. First, you gotta make the steel. A mix of scrap metal, iron ore, coke, and limestone gets dumped into the furnace, the raw ingredients for a future rail. The temperature in the blast furnace hits over 2,700 degrees Fahrenheit. That's 1,500 Celsius. Under that hellish heat, the metal turns liquid, glowing like the sun. Workers keep a close eye on the composition. Even an extra 0.1% of carbon can make the rail too brittle or too soft. After melting, the molten steel is poured into molds, metal forms that create rectangular blocks called ingots or slabs. They don't look like a rail yet, just solid bars a few meters long and over a foot wide. After pouring, each blank is cooled, but not completely. It's kept warm to reduce stress during the rolling process. This stage is the foundation for everything. If the steel comes out bad, even a perfect rolling job won't save it. So quality control here is almost a ritual. Chemists check the composition, metallurgists monitor the temperature, and automatic sensors track the cooling uniformity. Only when every single parameter is locked in does the blank move on, into the fiery heart of the rolling mill. In the rolling mill, massive billets, up to 20 meters long, are heated in furnaces to over 2,200 degrees Fahrenheit, 1,200 Celsius. The metal becomes pliable, like dough, but keeps its density and strength. The hot blank is immediately fed into reversing rolling stands. These are huge machines with heavy rollers. It passes through them several times, first to reduce its thickness, then to give it the right shape. Each pass is a squeeze and stretch, gradually transforming the metal from a simple billet into a future rail with its complex profile: the head, the web, and the foot. To get the exact geometry, they use a final sizing roll. It's like the final polish of the shape, with tolerances on this step not exceeding 0.3 of a millimeter. Right after rolling, while the rails are still hot, they go through a cooling process. They're either evenly blasted with air or left to cool on an open rack. It's crucial that the cooling is symmetrical, otherwise the metal could warp. To ensure a smooth, bump-free ride at high speed, individual rails are welded into long sections, up to 400 meters without a single joint. The main method is thermite welding. In a special mold between two rails, a gap of a few millimeters is left. A molten steel mixture, created by the reaction of powdered aluminum with iron oxide, is poured in. The temperature hits a scorching 4,500 degrees Fahrenheit, 2,500 Celsius. This molten metal flows into both parts of the rail and fills the joint area. When it solidifies, it creates a monolithic bond, stronger than the rail itself. After that, the excess metal is trimmed off, and the weld is ground down to a perfectly smooth level, without a single bump. Every joint is inspected, with ultrasound or eddy currents, to make sure there are no hidden micro cracks. These long rails are easier to transport than you'd think. They're either wound onto special drums or carried on platforms with pivoting supports. And on the construction site, the sections are joined again, this time by welding or using special bolted joints. The result is a continuous rail line that stretches for kilometers without a single click. The same silent glide we've come to expect on high-speed trains. But first, after rolling and welding, the rails are still alive. There's stress left inside the metal, and the grain structure needs to be stabilized. This is where heat treatment comes in, giving the rail its strength, wear resistance, and durability. And it looks almost like a metallurgical spa session. The rail is rapidly heated to high temperatures, around 1,800 degrees Fahrenheit, 1,000 Celsius. This is done in furnaces, tens of meters long, where the temperature is controlled to the degree. At this heat, the steel's crystal lattice shifts into a new state, austenite. But the main event starts after that. The rail is instantly cooled. Jets of high-pressure water are aimed along the head and web, the very parts the wheel rolls on. The temperature drops in a flash, and a new structure forms in the metal, martensite, an extremely hard, wear-resistant phase. But to avoid brittleness, the rail is slowly heated and cooled one more time. This balances the structure, relieves any extra internal stress, and ensures the rail can handle frost, heat, and thousands of trains a day. In the end, the metal holds its shape and withstands pressures of tens of tons per square inch without deforming. Before a rail hits the road, it goes through a whole series of tough tests, like it's trying to join an army of high-speed transport. In special labs, it's checked for strength, hardness, geometry, and internal defects. First up, ultrasonic testing. High-frequency waves are sent into the rail. If there's a microcrack or void inside, the signal bounces back and flags the problem. Then, hardness measurements along its entire length to make sure the heat treatment was uniform. At the same time, its straightness and profile are checked. Laser sensors scan every inch, detecting even tiny warps that could cause vibration or wear. And finally, bend and impact tests. A piece of the rail is loaded with pressure dozens of times greater than the weight of a train, to make sure it can handle any challenge on the route. When the rail has successfully passed all the tests, it's time for its most important journey, to the installation site. But how do you transport giant metal strips over 90 meters long? Regular trucks can't handle it. Here, they use special railway platforms with curved supports that reduce stress and prevent the rail from sagging or vibrating during transit. Sometimes, rails are transported already welded into even longer sections, from 400 to 600 meters. Before installation, the rails are heated or cooled depending on the ambient temperature. This is to compensate for the thermal expansion and contraction of the metal. Otherwise, it would buckle in the heat or gaps would form in the cold. In practice, each rail is laid with these physical changes in mind, usually at a stress-free temperature point. Every year, the world lays down over 1 billion tons of asphalt, the material that modern civilization would literally grind to a halt without. But few people know that every foot of road is the result of a complex alchemy of stone, fire, and oil. It all starts with an explosion in a quarry and ends with a hot, black mass steaming under the wheels of a roller. In this video, you'll see how asphalt is born, from blasting rock to the final roller that polishes a new road. And if you stick around to the end, you'll learn a secret that most drivers don't even know exists. Almost nothing goes to waste. That crushed old asphalt is then added to the new mix back at the plant. On average, new asphalt laid on our roads contains about 22% recycled material. The payoff here is huge, both economically and for the environment. First, it drastically cuts down on the need to quarry new stone and produce new bitumen, which saves natural resources and energy. Second, it makes the final product cheaper, saving billions of dollars from road maintenance budgets. So, every car trip you take is a journey on a complex piece of engineering that not only withstands massive loads, but is also a prime example of an industrial ecosystem where the old is constantly reborn into the new, closing the loop and making the country's infrastructure a little more sustainable. The story of asphalt doesn't start on the road. It starts in two completely different places. The first is a quarry. It's a massive wound on the face of the earth where rock is blasted out. It all begins with a loud explosion that shakes the ground for miles. Huge boulders break away from the rock face. Then, giant haul trucks with wheels taller than a person move in and haul these stone boulders to the primary crusher. This is a metal monster that crushes massive boulders into smaller chunks with its steel jaws and incredible force. But that's just the beginning. The stone then goes through a whole series of crushers and screens, giant vibrating sieves. The goal isn't just to crush the rock, but to carefully sort it by size. The result is entire mountains of clean, sorted stone, which we call aggregate. You've got everything here, from large, fist-sized rocks to fine crumbs and even dust, like sand. Each size is stored in its own separate pile. It's like in your kitchen, where you have flour, sugar, and salt, each ingredient separate, waiting for its turn. This is the skeleton of the future asphalt, making up 95% of its mass. The second place where asphalt is born is an oil refinery. When crude oil is processed into gasoline, diesel, jet fuel, and other light products, a thick, black, viscous substance is left at the very bottom of the distillation tower. This is bitumen. In its normal state, at room temperature, it's as hard as a rock. You can shatter it with a hammer. But if you heat it up, it becomes a liquid, like thick syrup. It's this property, being solid when cold and liquid when hot, that makes it the perfect glue for our stone skeleton. Bitumen is the soul of asphalt. It's black heart that holds everything together. Now, let's head over to the asphalt plant. This is where all the ingredients come together. From a distance, it looks like a complex tangled metal jungle. Tall silos, endless conveyor belts, pipes, tanks, and a central tower with smoke rising from it. It's a real factory that works like a single, well-oiled machine. Different sizes of aggregate are fed from separate bins onto a conveyor belt. But not just randomly. The whole process is controlled by a computer. An operator in a control booth inputs the exact recipe for the asphalt. Depending on where it's going to be used, a busy highway or a quiet side street, the recipe will be different. The computer knows exactly what percentage of large stone, medium, small, and dust is needed for the perfect mix. It's like baking a complex cake, where every gram counts. This mix of stones begins its journey up a long, inclined conveyor and enters the heart of the plant, the drying drum. This is a huge, long tube that slowly rotates, set at a slight angle. From one end, a powerful burner blasts a roaring pillar of fire inside, like a jet engine. The temperature inside hits 300 degrees Fahrenheit. The stone, slowly tumbling inside this drum, heats up, and most importantly, gets completely dried out. Moisture is the #1 enemy of good asphalt. Even a single drop of water can prevent the bitumen from sticking properly to the stone's surface. So, the stone has to be bone dry. After the drying drum, the hot, moisture-free stone is carried up by an elevator to the very top of the central tower. There, it passes through another set of screens for a final quality check on the sorting, and then falls into hot storage bins. Meanwhile, in special insulated tanks, our black glue, the bitumen, is being heated up. It's also brought to a high temperature to make it fluid and runny. And now comes the climax. The computer gives another command. A weigh hopper, with incredible accuracy, measures out the required amount of hot stone of each size from the different bins. Then, a precisely measured amount of hot liquid bitumen is sprayed into this superheated stone mix. This entire mass, stone and bitumen, is dropped into a mixing chamber, called a pug mill. It's like a giant kitchen mixer, but instead of whisks, it has two powerful shafts with metal paddles. These paddles churn the hot mass with enormous force, and in less than a minute, every single stone, every grain of sand, is coated in a thin, shiny film of black bitumen. Out of the chamber comes the finished asphalt, a uniform, steaming black mass with a characteristic oily smell. Now this hot, freshly made product needs to be stored until it's shipped out. It's lifted and dumped into special insulated storage silos. They're like giant thermoses that can keep the asphalt hot for many hours, sometimes even days. Dump trucks pull up under these silos. With a loud clang, a gate opens and several tons of hot asphalt pour into the truck's bed with a roar and a cloud of steam. The bed is always covered with a tarp to keep that precious heat in during transport to the paving site. At the construction site, the final act begins. The dump truck slowly unloads the hot mix into the hopper of a special machine, an asphalt paver. This machine, moving forward slowly, evenly spreads the asphalt over the road surface, forming a perfectly level layer of a specific thickness. At the back of the paver is a heavy, heated plate called a screed. It does the initial compaction and gives the surface its first pass of smoothness, but the asphalt is still soft and loose. To make it strong, it needs to be compacted. Right behind the paver follows a whole team of heavy road rollers. First come the large steel drum rollers, which use their immense pressure to squeeze the air out of the asphalt mix and force the stones to lock together tightly. Then, pneumatic tire rollers might be used, which knead the surface, making it even denser. And in the final stage, smooth steel drum rollers pass over it again to give the road its final, smooth finish. As the asphalt cools, the bitumen turns from a liquid back into a solid. It permanently glues all the stones together, turning the loose mix into a strong, waterproof monolith. After a few hours, the road that was recently hot and soft becomes hard and ready for traffic. And that's the whole point. From the explosion in the quarry to the heavy roller on the road, every stage of this process is designed to create a durable, reliable surface that will withstand thousands of cars every single day.
Every year, humanity extracts over 2 billion tons of iron ore from Earth's crust. Picture this. More than half of our planet's entire weight is iron, most locked in the core, creating the magnetic field protecting all life. But here's what shocks engineers worldwide. We're standing on the most abundant metal in the universe, yet accessing it requires temperatures hotter than volcanic lava. How does rust-colored rock transform into gleaming steel skyscrapers? How do ancient mountains become modern civilization? Stick around till the end. You'll discover why iron shaped human history more than gold ever did, and the jaw-dropping secret hiding inside every bridge, car, and building around you right now. The story begins in Western Australia's Pilbara region, where iron mountains stretch across landscapes older than dinosaurs. Massive excavators, standing 8 stories tall, picture buildings that walk, tear into rust-red cliffs with bucket teeth weighing 12 tons each. These mechanical giants rip through rock layers formed 3 billion years ago when Earth's oceans first rusted. With thunderous crashes echoing across 40-mile-wide craters, each excavator loads haul trucks carrying 400 tons per trip. That's the weight of 80 elephants moving at 40 miles per hour on tires taller than basketball hoops. Processing 30 million tons annually from single mines, enough iron ore to build 12 Golden Gate bridges every single day. Next comes crushing, where house-sized jaw crushers, imagine dinosaur mouths made of hardened steel, pulverize boulders into gravel-sized chunks. With deafening roars splitting eardrums even through protection, these crushers generate forces exceeding 20,000 pounds per square inch. Clouds of red dust billowing upward create artificial sunsets visible from space satellites. Conveyor belts stretching 12 miles long, longer than Manhattan, transport crushed ore at 18 miles per hour. Workers riding inspection carts traverse distances requiring 25 minutes one way. That's enough belt to wrap around 300 football fields. Every hour, 50,000 tons flow through this system, weight equivalent to 5 Eiffel Towers moving continuously past checkpoints. Giant grinding mills, standing 5 stories tall, with diameters matching Olympic swimming pool widths, pulverize rock into fine powder. Inside these rotating drums, 20-ton steel balls, each weighing more than shipping containers, tumble with ore, creating grinding thunder heard miles away. Operators monitor vibrations. Wrong frequencies mean catastrophic bearing failures, costing millions. At rotation speeds creating gravitational forces triple normal Earth gravity, particles shrink to powder finer than talcum. Processing 8,000 tons hourly, that's filling semi-truck after semi-truck every 30 seconds. This powder, called concentrate, contains 65% iron. Magnetic separators then extract iron particles using forces strong enough to levitate railroad spikes, leaving waste rock behind. Next comes the blast furnace, a towering inferno standing 30 stories high, its steel shell glowing dull orange even from outside. At internal temperatures exceeding 3,000 degrees Fahrenheit, hot enough to vaporize aluminum instantly, iron ore transforms into liquid metal. Picture Dante's Inferno engineered with precision. Measured charges of iron ore, coke, and limestone descend from the top, while superheated air blasts upward at 2,000 degrees from ring-shaped nozzles called tuyeres. This creates a raging chemical storm, where carbon monoxide rips oxygen from iron oxide molecules. The reaction releases enough heat to melt granite. Every 3 minutes, sensors check 20 different parameters. Without precision, furnaces explode with force demolishing city blocks. The blast furnace operates continuously for 15 years, never cooling, never stopping, like Earth's core relocated to industrial facilities. Inside this chemical reactor, materials descend through distinct zones. Upper regions preheat incoming ore. Middle zones drive off moisture and carbon dioxide. Lower depths become hell itself, where iron liquefies. At the hearth bottom, molten iron collects at 2,800 degrees Fahrenheit, dense as lead but flowing like water. Every 4 hours, workers drill through clay-plugged tap holes. Liquid iron erupts in blinding white rivers, flowing through ceramic channels into railroad cars holding 300 tons each. This step is critical because timing determines metal purity. Tap too early, slag contaminates. Too late, furnace pressure ruptures containment walls. After tapping, slag, lighter impurities floating atop molten iron, gets diverted into separate channels. This glowing amber liquid, essentially liquefied rock, contains calcium, silicon, and aluminum oxides stripped from ore. Rather than waste, it becomes roadbed material and cement ingredient recycled at 98% rates globally. The molten iron, called pig iron, contains 4% carbon, too brittle for construction. Picture glass that looks metallic. Drop pig iron from waist height, it shatters into fragments. Next comes the basic oxygen furnace, where pure oxygen blasted at supersonic speeds through 3-foot diameter lances burns away excess carbon in 17 minutes. Flames shooting 70 feet high, temperatures hitting 3,200 degrees, create hurricane-force winds inside steel vessels holding 350 tons of liquid metal. Steel making requires precision rivaling brain surgery. Computer-controlled oxygen flow adjusts by milliseconds. Operators add exact amounts of manganese, silicon, chromium, elements changing steel properties dramatically. Too much carbon, steel cracks in winter cold. Too little, metal bends under load. Picture this: alloying elements get injected via submerged lances. Electromagnetic stirring, invisible but powerful, homogenizes composition. Samples extracted every 3 minutes get analyzed via spectrometers, determining chemistry within seconds. Modern furnaces achieve carbon content accuracy to 0.01%, difference between skyscraper standing or collapsing. After refining, liquid steel flows into continuous casting machines producing slabs 30 feet long, weighing 25 tons, at rates of 1 slab every 90 seconds. This wasn't always so advanced. Back in ancient Anatolia around 1300 BC, Hittite metallurgists discovered heating iron ore with charcoal produced workable metal. That breakthrough, accidental furnace conditions reaching iron's melting point, changed human civilization forever. Iron tools outperformed bronze, enabling agriculture revolution. The breakthrough came when British inventor Henry Bessemer patented his converter in 1856, slashing steel production time from 24 hours to 17 minutes. Suddenly, steel costs dropped 90%. This single invention built modern cities. Skyscrapers, bridges, railroads exploded across continents. Today, global steel production exceeds 1.9 billion tons annually. That's enough to build 75,000 Eiffel Towers yearly, or manufacture 43 million automobiles, or construct bridges connecting every coastline on Earth. Carbon emissions drop by 62% when using recycled steel versus virgin ore, equivalent to removing 12 million cars annually. Industry saves over $80 billion yearly through scrap recycling. Processing costs drop 43% because melting scrap requires 1/3 the energy of blast furnaces. So here's the secret promised: every ton of steel you see, bridges, buildings, cars, will be recycled indefinitely. Unlike plastic decomposing into microparticles or paper pulping into mush, steel never degrades. Magnetic separation extracts it perfectly from demolished structures. That girder in your office building might contain steel from 1930s locomotives. Your car's frame could include battleship armor from World War II. Nothing disappears. Metal merely transforms, reborn eternally. From ancient mountains to modern marvels, cycle completes. Iron, humanity's most essential metal, circulates through civilization like blood through veins. We're not consuming Earth's iron, we're borrowing it, briefly, before passing it forward to futures we'll never see.
Every second, jet engines spinning at 12,000 revolutions per minute thrust hundreds of passengers across continents. But here's what defies physics. Inside those engines, Turbine blades made of nickel alloy operate at 3,000 degrees Fahrenheit, temperatures exceeding their own melting point by 200 degrees. Picture holding ice cubes in boiling water without them melting. That's the metallurgical miracle happening 35,000 feet above your head. How does metal survive temperatures that should liquefy it? How do engineers grow crystals larger than your hand from molten metal? Stick around till the end, you'll discover the jaw-dropping secret of single crystal manufacturing that eliminated metal's greatest weakness, and why a single turbine blade costs more than your car, yet lasts 20 years in literal hell. The story begins in specialized foundries where clean room standards rival semiconductor fabs. These facilities maintain air purity of less than 100 particles per cubic foot, 10,000 times cleaner than normal atmosphere. Even microscopic dust particles cause catastrophic flaws in turbine blades spinning at speeds where centrifugal forces generate stresses exceeding 70,000 pounds per square inch. That's pressure crushing steel like aluminum foil. Workers suit up in full-body cleanroom gear before entering casting halls. Inside, massive vacuum furnaces standing 2 stories tall and weighing 80 tons create environments replicating outer space. Vacuum pumps evacuate air until pressure drops to 1/1,000,000th of atmospheric pressure. At these conditions, materials behave differently. Impurities vaporize instantly. Gases trapped in metal escape, leaving behind purity impossible at normal pressure. Processing single batches costs $50,000 in electricity alone. Next comes mold preparation, where ceramic shells, think pottery on steroids, get built layer by microscopic layer. Technicians dip wax patterns shaped like turbine blades into ceramic slurry 10 times, waiting hours between coats. Each layer adds thickness thinner than human hair. After 20 days of coating and drying, workers melt wax away in autoclaves, leaving hollow ceramic molds with internal channels more complex than human circulatory systems. These molds contain passages narrower than spaghetti strands, designed to cool blades from inside during operation. Some channels measure just 0.008 of an inch across, thinner than credit cards. Manufacturing these passages requires such precision that lasers verify every dimension. One blocked cooling hole means blade failure at 300 degrees lower temperature. That's difference between safe flight and catastrophic engine disintegration at cruise altitude, scattering turbine fragments through fuselage like shrapnel.
Giant crucibles containing nickel-based superalloy. Mixtures of nickel, chromium, cobalt, aluminum, titanium, plus 6 other elements in exact proportions. Heat to 2,700 degrees Fahrenheit. Picture liquid metal glowing white like miniature stars captured in ceramic containers. This superalloy, developed through decades of research, contains more expensive elements per pound than fine jewelry. A single turbine blade uses materials costing $800 before any manufacturing begins. Robotic arms lower ceramic molds into this molten inferno with precision measured in thousandths of inches. Timing matters critically here. Pour too fast, turbulence creates defects. Too slow, metal solidifies prematurely. Furnaces tilt at exactly 2 degrees per second, filling mold cavities in 17 seconds. During this pour, metal temperature drops 300 degrees, requiring computer-controlled heating to maintain consistency. One temperature fluctuation of 5 degrees ruins the casting, wasting months of preparation.
Now comes the magic, directional solidification. The filled mold sits atop a water-cooled chill plate at 70 degrees Fahrenheit while surrounded by heating elements maintaining 2,400 degrees above. This creates the steepest temperature gradient in metallurgy, over 2,000 degrees difference across 6 inches. That's transitioning from Arctic to volcanic conditions in the space between your thumb and pinky. Slowly, incredibly slowly, a computer-controlled mechanism lowers the mold through the furnace at speeds of 6 inches per hour. Picture watching paint dry, then slowing that down tenfold. As the mold descends, metal solidifies from bottom upward in a razor-thin freezing front. This directional cooling forces crystal growth in one direction only, upward, eliminating horizontal grain boundaries where cracks normally form. The process takes 14 hours for a 4-inch blade. Rush it by even 10% and polycrystalline grains form, destroying blade strength. But here's where physics becomes art. At the mold bottom sits a grain selector, a corkscrew-shaped passage so narrow only one crystal nucleus fits through. As metal solidifies upward, countless tiny crystals form at the chill plate. They compete, growing upward like metallic trees racing toward sunlight. Most hit the spiral walls and stop. Only the perfectly aligned crystal, the one matching the spiral's orientation, passes through this metallurgical gauntlet. This step is critical because it ensures the entire blade, every atom from root to tip, belongs to one continuous crystal lattice. No grain boundaries exist anywhere. Normal metals contain millions of grain boundaries per cubic inch. Single crystal blades contain 0. Without boundaries, there are no weak spots where atoms slip past each other under stress. The crystal structure extends uninterrupted through the entire blade like a 3-dimensional molecular Kevlar vest, with atoms locked in perfect geometric formation. After solidification, blades undergo solution heat treatment at 2,200 degrees Fahrenheit for 2 hours, then quench in inert gas. This locks crystal structure permanently and precipitates microscopic strengthening phases throughout the lattice. Next comes aging heat treatment, multiple cycles at precisely controlled temperatures that cause nanoscale particles to form. These particles, called gamma-prime precipitates, occupy 70% of the alloy's volume. Picture this. Imagine a 3-dimensional checkerboard where hard particles pin the crystal lattice, preventing atoms from sliding. These precipitates remain stable at temperatures where other metals liquefy. They're the secret allowing nickel alloys to maintain strength at 3,000 degrees, temperatures where aluminum vaporizes, titanium melts, and even steel becomes taffy. The heat treatment process takes 96 hours of precise temperature control. Deviate by 15 degrees at any point and mechanical properties drop 40%.
Coating application transforms already sophisticated blades into thermal protection systems. First, a metallic bond coat, aluminum-rich alloy, gets applied via high-velocity plasma spray at 20,000 degrees Fahrenheit. Metal particles accelerate to twice the speed of sound, impacting the blade surface with such force they cold weld instantly. This creates a rough surface for subsequent layers while providing oxidation resistance. Then comes the thermal barrier coating, yttria-stabilized zirconia ceramic applied atom layer by atom layer using electron beam physical vapor deposition. In vacuum chambers, electron beams vaporize ceramic ingots. The vapor condenses on rotating blades, building up a coating 0.08 of an inch thick with a columnar microstructure full of microscopic pores. These pores act like thermal insulation, trapping air pockets that reduce heat transfer. The ceramic coating lowers blade temperature by 400 degrees, the difference between survival and meltdown. Modern engines couldn't exist without this coating technology. This wasn't always possible. Back in 1940, early jet engines used cast iron turbine blades lasting 20 hours before failure. Temperatures barely reached 1,400 degrees Fahrenheit.
The breakthrough came when Pratt & Whitney researcher Frederick Vierling invented directional solidification in 1966, eliminating transverse grain boundaries and doubling blade life overnight. The true revolution arrived in 1982 when General Electric and Pratt & Whitney independently perfected single crystal casting. Turbine inlet temperatures jumped from 2,000 degrees to 3,000 degrees Fahrenheit, a 50% increase enabling massive efficiency gains. Modern turbofan engines achieve fuel efficiency triple that of 1960s designs. Today, advanced engines like the GE9X powering Boeing 777X aircraft operate at 3,200 degrees, with pressure ratios reaching 60-1. These engineering advances cut aviation fuel consumption by 65% per passenger mile over 50 years. Carbon emissions dropped by 12% when replacing older turbine blades with modern single-crystal versions in existing engines, equivalent to removing 18 million cars annually from global fleets. Airlines save over $47 billion yearly through improved fuel efficiency. Maintenance costs drop 58% because single-crystal blades last 3 times longer than conventional ones. So here's the secret promised. These blades don't actually survive above their melting point through material strength alone. They're actively cooled by air bled from the compressor, flowing through those microscopic internal channels at supersonic speeds. This cooling air, already compressed to 400 degrees Fahrenheit, seems hot by human standards but runs ice cold compared to the 3,000-degree combustion gases outside. Combined with ceramic coatings reflecting heat like mirrors, the actual metal temperature stays below 2,000 degrees, hot enough to glow orange but survivable. From molten metal to flying miracles, cycle completes. Single crystal turbine blades represent humanity's most sophisticated metal casting achievement. Objects where every atom's position matters, where crystal orientation determines survival, where manufacturing tolerances make computer chips look crude. We've engineered metal to survive in conditions nature never intended, creating materials that work at their physical limits. That's not just manufacturing, that's molecular architecture enabling the modern world's ability to shrink distance itself.
Every year, millions of tons of chemicals are produced worldwide, but one of them, chlorine, is truly staggering in scale. In the United States, over 12 million tons of this gas are made annually. That's the same weight as 120 Gerald R. Ford aircraft carriers, the heaviest ships in the world. But where does this dangerous, yet vital substance come from? It all starts not in a lab, but in underground deposits of common salt. From there, it involves electricity, membranes, and an entire industry that consumes more power than entire American states. And if you watch till the end, you'll discover the secret that chlorine hides behind its sharp smell. The United States is one of the world's largest producers of chlorine. Each year, plants in the country produce over 12 million tons of the gas. This number is just hard to wrap your head around. Imagine the weight of the aircraft carrier, the Gerald R. Ford, the heaviest warship in the world. It's about 100,000 tons. This means that in a year, American industry produces as much chlorine as 120 of those aircraft carriers weigh. This enormous quantity makes chlorine one of the top 10 most produced chemicals in the country. It all begins not in a laboratory, but deep underground. The main ingredient for our recipe is common rock salt, or sodium chloride. But it doesn't arrive at the plant in salt shakers. It's either mined in the form of huge chunks, or, far more efficiently, pumped out from under the ground. Water is pumped into deep underground salt deposits. The water dissolves the salt, creating a saturated salt solution called brine. And it's this concentrated, salty as tears solution that is our raw material. But it's still impure. It's full of contaminants, calcium, magnesium, and other minerals that can clog up our expensive equipment. So before the main show begins, the brine goes through a thorough purification process. It's passed through a whole series of tanks where chemicals are used to precipitate and filter out all the impurities. What comes out is a perfectly clean, clear, and very salty solution, ready for the main event, electrolysis. Now, let's head to the heart of the plant, the so-called cell room. This is a huge loud hall filled with rows of strange enclosed tanks connected by a network of pipes and thick electrical cables. These are the electrolyzers, or cells. This is where all the magic, or more accurately, all the chemistry will happen. Let's imagine one such electrolyzer. Essentially, it's a box into which our pure salt solution is poured. And into this solution, two electrodes are submerged, a positively charged anode and a negatively charged cathode. Now, a direct electric current of colossal power is applied to these electrodes. And this is where the split begins. The salt molecule in the water breaks down into positively charged sodium ions and negatively charged chloride ions. The electric field forces them to move. The positive sodium ions are drawn, as if by a magnet, to the negative cathode, and the negative chloride ions to the positive anode. And it's at the anode that the whole point of the process occurs. Each chloride ion that sticks to the anode gives up its extra electron. Two such chlorine atoms, having lost their charge, immediately pair up, forming a molecule of chlorine gas. Billions of these molecules gather, and tiny bubbles of a greenish-yellow gas begin to appear on the surface of the anode. This is our chlorine. The main resource for chlorine production is electricity. The chlor-alkali industry is one of the largest consumers of electricity in the entire US manufacturing sector. To produce 1 ton of chlorine, it takes about 2,500 kilowatt-hours of electricity. Now, multiply that by 12 million tons a year. It turns out that this industry consumes about 30 billion kilowatt-hours annually. That's more than the annual electricity consumption of entire states, like Vermont or Wyoming. It's like an entire city of 1 million people, working year-round just to split salt molecules. But what's happening at the cathode? The sodium ions have drifted over there. But they don't turn into metallic sodium. Instead, the electric current splits the water molecules in the solution into hydrogen and hydroxide ions. Bubbles of pure hydrogen are released at the cathode. That's our first byproduct. And the hydroxide ions left in the solution combine with our sodium ions to form sodium hydroxide, or caustic soda. This is our second, incredibly valuable byproduct. But here, a huge problem arises. We've just created 3 substances: chlorine, hydrogen, and caustic soda, and they must never be allowed to mix. Chlorine and hydrogen together form an explosive mixture, and chlorine and caustic soda react to form bleach, which is not what we want at all. So, the genius of the technology lies in separating these 3 products at the very moment of their birth. This is done using special membranes or diaphragms. Imagine a thin, paper-like, but very clever partition standing between the anode and the cathode. This membrane, made of a special polymer, is like a bouncer at a nightclub. It allows the positive sodium ions to pass through to the cathode, but blocks the negative chloride ions, preventing them from getting into the cathode space. This way, chlorine is born and collected in one part of the cell, while hydrogen and caustic soda are in another. Now we need to collect our harvest. The moist, hot, greenish-yellow gas is continuously pumped out of the anode chamber. First, it needs to be cooled. It's passed through heat exchangers where it gives off its heat. Then, it needs to be dried. Chlorine is incredibly aggressive, especially when wet. It corrodes almost everything. But there's one substance it doesn't touch: concentrated sulfuric acid. So, the wet chlorine is passed through towers where it bubbles through sulfuric acid, which, like a sponge, absorbs all the water from it. The resulting dry, cool, but still gaseous chlorine is ready for the next stage, liquefaction. It's compressed under enormous pressure and cooled at the same time. Under this double whammy, the gas turns into a clear, amber-yellow liquid that looks like oil. This liquid chlorine is much easier to transport and store. It's poured into special thick-walled steel tankers, or rail cars. Every step of this process is carried out under completely sealed conditions, because a leak of this gas is deadly. And what about our byproducts? They are no less important. The hydrogen we've produced is collected, purified, and used either as fuel for the plant itself, or sold for ammonia production, or in the food industry. And the resulting caustic soda solution is pumped out, concentrated by evaporating the excess water, and sold. It's one of the most important products in the chemical industry, used to make soap, paper, aluminium, and much more. And so, from simple salt water, by passing a huge amount of electricity through it, we learn to obtain 3 extremely important substances at once, which form the foundation for thousands of other products that surround us in our daily lives. Now let's see where all this enormous amount of chlorine goes. You might think it all goes into disinfecting swimming pools, but that's just a drop in the ocean. In fact, less than 5% of all chlorine is used for water disinfection. So where does the other 95% go? It's a key building block for other products. About 40% of all chlorine goes into the production of this universal plastic. The vinyl windows in your house, water pipes, medical IV drips, vinyl records, the credit card in your wallet, all of these were born thanks to chlorine. Another 40% or so is used to create thousands of other organic and inorganic compounds. Pharmaceuticals, solvents, refrigerants, herbicides, insecticides, the list is endless. Chlorine is also a key component for bleaching paper, giving it that clean white color. And finally, about the byproducts, which are actually no less important. We remember that for every ton of chlorine, we get about 1,100 tons of caustic soda. This means that American industry produces over 13 million tons of this vital alkali annually. This makes chlor-alkali production a perfectly balanced business. When the demand for one product falls, the demand for the other can rise, allowing plants to operate stably. So these millions of tons are not just statistics. They are proof that this sharp, suffocating gas is the invisible foundation for a huge part of the American economy. From the plastic pipes under our streets to the medicines in our pharmacies.